Hi everyone, welcome to a new video on practical navigation from Captain Subramaniam's series. This is from exercise 19, question number 1. The topic is long by Chron, and the celestial body used here is going to be a planet. So let's get into the question. The question says it's 17th of January 1992. It's AM at ship. That means it's morning on your ship and it's 17th of January. The dead reckoning position is provided. Lat and long, the sextant altitude of the planet Venus was 19 degrees 48.6 minutes. The chronometer was showing a time of 11:41:44 and the error was 2 minutes 06 seconds fast. If the index error was 2.1 on the arc and height of I was 12 meters, you have to find the direction of the position line and a position through which to draw it. So when they say a position through which to draw it, in this case of long by Chron, you have to basically find the longitude. So let's solve the ambiguity of the chronometer time first. So when the chronometer time is given to you, remember to write the time firstly as it is. In this case, of course, it's 11:41:44, and then add 12 hours to that time. Because again, I am repeating myself here. When you look at the time on a chronometer, it's like an analog watch with hands on it. So when you look at the clock, you don't know it's 11:41 in the morning or 11:41 at night, which would make it 23:41:44. So to solve the ambiguity of the chronometer time and to find out what is the date and time at GMT, uh, this is what we do. All right, so we write down two scenarios. So then we have two scenarios of chronometer time and we'll figure out which one is the correct one. All right, so then we apply the error. The error was fast, so if the error is fast, you will subtract the error from the given chronometer time in both the cases. Just simply put the values in the calculator, you should be able to find the answer. And then we get the GMT, and then we apply the zone. Now if the zone is east, because the longitude is east, we will add. If the zone is west, that is the longitude is west, we would have subtracted. All right, so again the zone is east. What is the zone time? The zone time is basically the longitude in time rounded off. So how do you find the zone time? Well, you just find the longitude in time, which is LIT, by dividing the longitude by 15, and you get 6 hours 40 minutes and 40 seconds, and then you round it off to 7 hours, which is the closest time. So some books will show you GMT and then LIT and then LMT. But the method I use is I use GMT, zone, and then ship's time. It doesn't make a difference. At the end of the day, you are trying to determine the ship's time to find out what is the correct GMT date and time. So we take the zone time. So if you are in east longitude, you will add it to the GMT. If you are in west longitude, you would subtract it from the GMT. So in this case, you add it to the GMT. So when you add it to the GMT, you get two scenarios of the ship's time. One is 18:39:38 and the other one is 6:39:38. Now you must be wondering, if 23 plus 7 is 30, why have I written 6? So it cannot be 30 hours on the clock. So when you get 30, just subtract 24 from it and you should be able to find out the correct ship's time. So there are two scenarios of ship's time. So let us go back to the question and see what is the hint given to us. The hint given to us in the question is that it is AM at ship. So it's 17 January and AM at ship. So the second case would be the correct case, right? So that is the correct case. So if it is 17th January on the ship and it's morning, so I will write 17th January here, right? And I am 7 hours ahead of GMT. That means at GMT, the date is still 16th of January, 11 o'clock at night. And on my ship, I am 7 hours ahead of GMT. It's already 6 in the morning, but the following day, which is the 17th of January. That is why the correct GMT date and time is 16th of January, 23:39:38. All right, so at GMT at UK at 000 degrees longitude, the date is 16th of January, 23:39:38. I am 7 hours ahead. My longitude is 100 degrees 10 minutes east. So I will add 7 hours to the GMT time to find out that the time on my ship is 6:39:38 in the morning. It's 17th of January. And so the GMT is 16th January. That is the date and time I will use. All right. Having said that, let's start finding out the values. So let's start with the left hand side first. So we've got GHA increment, V correction. Let us find out how do we find those values out, as well as the declination. So we have to find out the values for 16th of January, 23, 39, 38. So I will go into the almanac and show you how to find the different values at one point of time. Hopefully I don't have to come back and forwards too many times, otherwise it gets a bit boring for you guys who are watching the video at home. So I will go into the almanac here. So 16th of January, 23, 39, 38. So 16th of January should be somewhere early into the almanac. All right, so we've got 16th of January here, 23, 39, 38. Remember, the planet is Venus. So here you go. So this is Venus here on your left hand side. You can see Venus here, 16th of January. Let me switch on my pen here. 16th of January, 2300 hours. All right, so if you can see here, this is 2300 hours. Venus is here. So you can see the Venus. This is the GHA of the Venus. And the declination is given to us as 21 degrees 30 minutes south. All right, this is the GHA and the declination. And then if you go down the columns, at the bottom of the column you have the D correction given for declination. So for that, make a note whether your declination is increasing or decreasing to the next hour. So if it is increasing, that means I will find out the D correction value and add to it. This is just the D value at the bottom. All right, similarly, we have a V correction this time for planets. This is for the GHA. So here, the V correction is negative. So if the V correction is negative, I will go back into the increments page for 39 minutes and 38 seconds, find out the V correction value and apply it as a negative correction, because the sign of the V correction will tell me whether it should be negative or positive. So these are some of the values I find out from here. So now I will go back into the nautical almanac increments page 39, 38. So if I go back into 39 and 38, so you can see here 39 and 38. 39 and 38. So firstly I will find out the increment. So 39 minutes and 38 seconds. So this is my increment correction. All right, this is my increment correction for planets, sun and planets in the same column. And for D and V value, so we go back and remember the D and V value. 16th of January, 16th of January. So remember, the D value is 0.3 and the V correction value is 0.8. These are the values for which you have to find out the correction on the page of 39 minutes and 38 seconds. All right, so here you have 0.3 and 0.8. You will go into the V or D correction value. So for 0.3, that is your declination, your value will be 0.2, and for 0.8 your value will be 0.5. So 0.5 is for GHA and 0.2 is for declination. So this is how you find out the values that I will be now showing you back on that page there. So you can see here, this is how I found out these values here. V correction, remember the V negative 0.8, you found out 0.5 and it will be a minus, and the increment is always added. So that is how I found out. Similarly, declination, remember 21 degrees 30 minutes was the initial correction. D value 0.3 from the bottom, 0.2 was the correction value at 39 minutes and 38 seconds, and you found out the corrected declination. So declination correction was added because the declination was increasing from 23 going to the next hour, and V correction was subtracted because the sign of the V tells us what correction to apply and how to apply it. All right, now we come to the right side of the page where the sextant altitude is actually given to us in the question. So we write it down the way it is. Then the index error is given to us as on the arc 2.1. So we will take that and subtract it off. Then we find out the height of eye, which is the dip for 12 meters. So how do we do that? We go back into the almanac for 12 meters of height of eye. 12 meters of height of eye. So in your almanac, the first page is this page here. So this is your height of eye correction, 12 meters. So 12 meters, you don't need to interpolate. You can just find from here is minus 6.1. All right, so 12 meters lies between 11.8 and 12.2 minus 6.1. So you go back and say I have put 6 minus 6.1 there. So when you subtract the dip correction from the observed altitude, you get the apparent altitude. So when you get the apparent altitude, remember the value 19 degrees 40.4. And in this case, of course, we have a total correction, but we also have a additional correction, so I will have to show you how to find that out as well. So remember, this is a total correction and there is an additional correction as well. So you can see I have written below the apparent altitude value, there is a total correction and there is an additional correction. So we go back and find out how to find that out. So 19 degrees 40.4 and it's 16th of January. So we go back into the same page from where we found the dip correction. You can see here the middle column is for stars and planets. So the apparent altitude value is down this column here. So for 19 degrees 40.4 will be somewhere here, and you get the correction minus 2.7. This is the total correction. But for planets like Venus, you have an additional correction depending on the month in which you have taken the site. So here the additional correction is because 16th of January lies between January 1st and February 2nd, your correction will be 0.1, especially if your apparent altitude value is between 0 to 60 degrees, which in this case it is because our value is 19 degrees 40.4 minutes. So you also have to take this correction along with you, 0.1 as well and negative 2.7. So here I have applied negative 2.7 and 0.1. You can see negative 2.7 and 0.1. You apply both of them all under the minutes column, not under the degrees column. All right, you get the true altitude, you subtract it from 90 degrees. So you subtract true altitude from 90 degrees and you get the true zenith distance. So of course it's not a negative number, zenith distance cannot be negative. So when I say subtract it from 90, so 90 is the bigger number, so you will subtract it from 90 and you get the true zenith distance. All right, so although you don't apply the true zenith distance anywhere else in this question, it is normally used for the PZX triangle, or it is used to draw the rational horizon diagram. So if you're wondering why we have found that out and not used it anywhere, you will figure it out when you start drawing diagrams. All right, so then what we do is we use the formula here given to us, cos p equals sine true altitude plus minus sine lat or sine declination. So there is a minus here as well and we have to choose either plus or minus. Now how do we choose either plus or minus is depends on the name of the declination and latitude. So if the declination and latitude are different names, in this case one is south and the other is north, we will use plus. If they were both same names, if they were both south or both were north, I would have used minus. So in this case one is south and the other is north, so I will use plus only. So you can see here sine true altitude plus sine latitude multiplied by sine declination divided by cos of latitude cos of declination. Put the values as you see I have put and then figure them out correctly. Remember, when you are putting the values in the calculator, be very careful when you are putting two values together. So some people, what they do is they put the entire equation in the calculator without using the brackets. And in that case, your calculator gets confused at times and gives you the wrong answer. If you are an expert, you have tested it out, make sure you have done it the correct way. The values should be matching the values I have put here on the page to get the right answer. So once you get cos p equals 0.66748, shift cos inverse, your p value should be 48 degrees 7.6. Now in this case here, students get confused, is this p or is this LHA? So the only way to solve it is by using a diagram. So when you solve using a diagram, you get the correct answer and you figure it out. So what happens here is that you have a circle, draw a circle, draw a straight line, call it the celestial Greenwich meridian. All right, then you look at the GHA value. What is the GHA value? The GHA value is 211 degrees 30.5 minutes. That means you have to measure it westward. That means west is always on the left and east is on the right. So you measure it westward. I will use a black pen first. So go westward and measure out 211 degrees. Again, you don't have to do it to scale. You can see here, this is the way I have done it, and I will call this Venus. All right, this is 211 degrees GHA measured westward from celestial Greenwich planet, celestial Greenwich meridian, and this is 211 degrees. What was the exact value? 211 degrees 30.5 minutes. All right, now I will change the color of the pen. The only thing I can plot here is my longitude, which was 110 degrees 10 minutes, and that is east. Now remember, this is an approximate longitude, but still it gives us an idea of where we would be. So 110 degrees 10 minutes east, because it's east, I will measure it from the east going towards Greenwich. From the Greenwich meridian, I will measure it towards the east. So somewhere here would be me. This is me, observer. All right. This is my longitude of 110 degrees 10 minutes, and my GH is of course 210 degrees 30 minutes. Is that right? 210 or is it 211? I can't remember. 211 degrees 30.5 minutes. All right. So you have plotted yourself and you have plotted the planet as well. Now, what is the LHA? LHA is measured westward from the observer all the way to the celestial body. This angle here. This is the LHA. The red part here is LHA. Now, LHA can in this case LHA be equal to P? P is only 48 degrees, whereas LHA here you can easily see is more than 300 degrees. So that means here, and you can measure it out by approximation, you can measure it out. I don't want to get into it, otherwise you will get confused, but you can work it out yourself, right? Because we know the values here. We know one is 211 degrees 30 minutes, longitude is 110 degrees 10 minutes. I can figure out what this is. So if I use my common sense here, this here, this angle, so we can find out this cannot be I mean I can figure out the red part of it, right? So sorry, not the green but the red part of, so I can figure out the red part. All right, so it is definitely more than 300 degrees. I can see that clearly. So it can, so in this case P cannot be equal to LHA, right? So that means LHA is equal to 360 degrees minus P in this case. So that means 360 degrees minus 48 degrees 7.6 minutes, which will give you 311 degrees 52.4 minutes. Because my diagram has told me that my LHA is clearly more than 300. It is not 48 degrees for sure. I can see that, right? So if it is not 48 degrees, then means it has to be LHA is equal to 360 minus P. Simple as that. My diagram has told me. So I will do that. So I have found out the LHA. Now, once I have determined the LHA, that is the LHA I will use here. And I will forget about the letter P. I will not use P anymore to confuse myself. Alright, so GHA, LHA, subtract one from the other. Always subtract the smaller number from the larger number. There are no negative answers here. Now, if GHA is more than LHA, if GHA is more than LHA, longitude will be west. If LHA is more than GHA, sorry, I've just written the same thing again. If LHA is more than GHA, then we have east longitude. In this case, LHA is more. So GHA least, longitude east. GHA best, longitude west. So here LHA is more, LHA is more, GHA is least, longitude is east. So I will subtract one from the other and get east longitude. Main portion done. That is the position through which the position line will pass. And then simply you have to find out A, B and C. A is equal to tan lat by tan LHA. Put the values of tan lat and the LHA value. LHA value is 311 degrees 52.4 minutes. Alright, so even if you put the P value, you will actually get the same answer, except that you might get a negative or a positive. But put the LHA value, 311 degrees 52.4 minutes. Tan lat, you know the latitude already. You will get 0.55. In case you get a negative answer with A and B, ignore the negative sign. Never put a negative number with A, B or C because we label them. So how do we label A? A is named opposite to latitude. Named opposite to lat unless LHA is between 90 to 270. What is your LHA? 311. It is not between 90 to 270. So you will name it opposite to latitude. Latitude was north. Your latitude was north. Go back and see. Latitude was 31 degree 41 minutes north. So you will name it south. B, same as declination. Declination was south. So I will name it south. And how do I find out B? Tan declination divided by sine LHA. Again, LHA is 311 degrees 52.4 minutes. You know declination already. Put the values. You may get a negative answer. Ignore the negative sign. Alright. And you find out the value. And then how do you find out C? C, if both are same, A and B are same, they will add and use the name of their own. So A and B, 0.55 plus 0.53 is 1.08 and they are both south. So I have named C south. Then tan azimuth is equal to 1 divided by C times cos lat. Put the value of C, 1.08 and cos lat. You know already how to do that. Check the values as I have found out the values. You can see at every stage I write the values. Why do I do that? Because if I make a mistake, then I can retrace my steps and find out exactly where I went wrong. Because when you're solving a long question like this, it is quite possible you will make a mistake somewhere. I make it all the time. That's why I solve the question before I bring it to you. If I solve it live, trust me, I will be making many mistakes. All right. So always write down your steps, write down the value so that you know how to find that out. So once you find out tan azimuth equals oh sorry, 1.8809, shift tan inverse of this value 1.08809, you will get 47.4. All right, now you have to label 47.4. 47.4, how do you label it? Name of C, this is same as C, and this is same as LHA. So C, as you know, was named south, easy. But how did I name LHA? So remember, 0 to 180 LHA is west, and greater than 180 is to 360 is east. So LHA was 311. So that is why I have named it east. Now what is south 47.4 east mean to you? South 47.4 east means that if I am in south, which is 180, and I am going towards east, which is 090 degrees, I go 47.4 degrees towards east. That means 180 minus 47.4, which is equal to 132.6. Now in my case here, my students, I asked them to round off these numbers because these are all bearings and you have to use them for plotting. You cannot plot 47.4 degree, 132.6 degrees. You can't do that. So you round it off. But I sometimes keep it like this because the answer in the book is the in decimals. That's why. All right. So anyhow, your true bearing is 132.6 degrees. This is your true bearing. All right, and then how do you find out your position line? Minus 90 plus 90. So if you minus 90, you get 042.6 degrees, and if you plus 90, you get true to 2.6 degrees. So that is the orientation of your position line, your PL. All right, that is pretty much the question. I don't want to make it any longer than already it is. So I hope these videos are helping you guys. Please let me know in the comment section. The least you can do is give me a like, thumbs up, or put a comment in the comment section letting me know how I'm going. Thank you for supporting the channel. Thank you for your like, comments, share, subscription, membership, and I will see you soon with my next video. The video that explains this question in Hindi, the link to that is in the description section below. Please watch that if you understand Hindi. Thank you and bye for now.